This is a lesson on torque and the second law of motion. I'm taking a moment to review several concepts that we've covered in previous lessons that are adding together as we head deeper into rotational dynamics. And the first is that the linear quantities that we studied for basic motion, displacement, velocity, and acceleration, had rotational equivalences. There's angular displacement, there's angular velocity, there's angular acceleration. With the idea of angular acceleration established, we moved towards rotational kinematics, where we saw everything that we learned in linear kinematics had a rotational equivalency. All of these equations here could be easily translated into a rotational version. With all of those ideas developed, we can now look at Newton's laws and how they relate to motion. And just like a net force causes a linear acceleration, you won't be surprised to find out that a net torque causes an angular acceleration. And so you can see the analogy from linear to rotation for these quantities. Torque is the rotational analogy of force. Moment of inertia is the rotational analogy of mass. And angular acceleration is the angular version of acceleration. Okay, so there's some elegance mapping from this one equation to the other. And if you understand Newton's second law and how to find quantities, solve problems, apply the concept of Newton's second law in rotation will not be that difficult for you to pick up. Of course, we're going to be looking at net torques. We're going to take many torques on a body and add them all together. We have a moment of inertia, which I had covered in a previous lesson, and you can refer back to how to find a total moment of inertia or how to use the parallel axis theorem in order to find the moment of inertia for an object that isn't being rotated about its center of mass, but some distance d away from the center of mass. When I consider those things, I will get the acceleration of a rotating object. As we move towards problem solving with Newton's second law in rotational motion, we will need a strategy for how to apply the concepts consistently in order to have equations develop in order to solve. So, always draw a general sketch. Once you get your general sketch drawn, draw an extended free body diagram. You're used to drawing free body diagrams. In this situation, because we're dealing with torque, we need to draw an extended free body diagram and really locate on the object where that force is being applied, because distances matter. So draw an extended free body diagram and be precise and label in here maybe distances or angles that you will need later in the problem. This will be your tool for developing equations. Once you've identified all your forces, be sure to assign a coordinate system. And I've noted here that we're going to need 3 dimensions because we have torque and right-hand rule causes us to have a 3rd dimension in or out of the page. You will want to denote which direction is positive. By convention, you can see the coordinate system here, x, y, and z, with z out of the page being positive. You could draw an equivalent system that looks like this, x, y, and then draw the dot for coming out of the page for z. That would be a perfectly fine coordinate system as well. And that way, when you get clockwise or counterclockwise torque, which result in right-hand rule being into or out of the page, you can denote it with a positive or negative sign in your equations, just like you did for x and y components. Now apply Newton's second law. You have your diagram going, and it's your tool to be able to write these equations out. Always do a linear Newton's second law. You can see in this situation, I have only up and down forces, so it's easy for me to get a relationship going among those forces linearly in x or y direction. If you have 2 dimensions, you can do an analysis in the x direction separate from an analysis in the y direction, similar to what you've learned applying Newton's second law of motion for linear. The addition for torque analysis is doing the rotational version of Newton's second law, where you write out net torque equals I alpha. In this situation, you will assign a pivot point on your free body diagram, which is the center of the circular motion. From that point, you can calculate torques and relate it to the moment of inertia and the angular acceleration in order to apply this new concept in the torque analysis. I'm going to remind you of this idea I brought up a little bit earlier in the lesson, how there's a linear equivalent to angular acceleration. That's how you can relate your equations from the linear dimension, Newton's second law, to your rotational dimension of Newton's second law. Alpha here is related to the acceleration here with this equation. Once you have your equations set up, you can identify your knowns and unknowns, you can identify how your algebraic strategy will go, and you can solve. When you get done, reflect on your answer and problem solving. The first problem I've chosen for us is a problem that we began in the moment of inertia lesson, the stacked disks. And in that lesson, we determined the moment of inertia of the two-disk system. There's one disk on top of another, is given by this value. A smaller disk is placed on a larger disk, which is attached to a frictionless surface and allowed to pivot about its center. So I have a picture over here. Here's the pivot and the center, and there's one disk on top of the other, and this is a top view. Okay, so we're looking down at the two disks. The mass and radii are given. The string is wrapped around the larger disk and is pulled with a force of 40 newtons. So the string is pulling here with a force of 40 newtons, and I'm going to note that the whole system will rotate in the counterclockwise direction. And I'm going to assign a coordinate system already because the center of mass of this thing isn't moving. It's pinned down. I can assign X and Y, but I don't think I'll need to decompose any force. But what I will need is a direction for the torque. And so I'm going to have Z out of the page. I'm going to note if I do right-hand rule, I have the counterclockwise direction, which results in my thumb out of the page, and the torque will be positive out of the page for this force. It says, what is the magnitude of the torque applied by the force? So we'll start there. The torque applied by the force is going to be RF sine theta. So the radius for the force is going to be the radius of the larger disk, which I will call R1. There's a radius for the smaller disk, R2. So this will be R1. The force is F, and the angle between them is a 90-degree angle, so I'm going to put sine 90 degrees here. So RF sine 90, sine 90 is 1, so I can put R times F here. The radius is 0.7. The force being applied is 40. And when I multiply those two together, I get 2.8 newtons times meters, and that's the torque being applied by this force. Okay, part B says, what is the magnitude of the angular acceleration caused by the torque? So we have the torque, and we have the moment of inertia, and they're asking us for angular acceleration, so we're going to apply Newton's second law. The torque has to equal I times alpha, and we're solving for alpha. Alpha equals the torque divided by I. The only torque being applied is by this one singular force, which we know the torque for, which is 2.8. I, the moment of inertia, we calculated previously, 1.385. And when you run this through your calculator, you get an angular acceleration of 2.022, and this is radians per second squared. Part C, what is the linear acceleration of the point labeled A on the diagram? So when I look at this, the angular acceleration describes the acceleration rotationally for all of the points for both disks, on both disks. All of the points everywhere rotate in the same angle in the same amount of time and are speeding up at the same rate. So they all have this angular acceleration, 2.022. What the problem is asking is, what's the linear acceleration at this point A? Linear acceleration is given by A equals alpha r. So I can relate this angular acceleration to the linear acceleration. Well, the r I need here is the radius of the smaller disk. So I will take 2.022 and multiply it by 0.4. And when I do that, I get a tangential acceleration of 0.8087. And this is meters per second squared. When you take radians per second squared and multiply by meters, the radians, which are dimensionless, cancel, and the meters kind of take over there. The next problem I picked out for us is one you will commonly see in solving problems that involve torque. And it's simple machines involving a pulley. A pulley is used to lift objects, and what we're going to consider is that pulleys have a mass and dimension that can be taken into account in force analysis by examining the torque rotating the pulley. It takes some sort of torque to rotate that object. Because it has inertia, there must be some force causing it to turn. We're going to treat a pulley approximately as a disc. Consider the simplest case of a pulley, a single rope wrapped over the pulley. Let the pulley have mass 13.6 kilograms and a radius of 20 centimeters. A 50 kilogram object is attached to one end. What force must be applied to the free end in order to? Okay, and there's three situations here. Just barely lift the mass with constant speed, and lift the mass with 4.9 meters per second squared acceleration. Okay, so that's an acceleration. That's a linear acceleration, 4.9 meters per second squared. Just barely lift the mass and lift the mass with constant speed, to me, both mean that the acceleration is 0. Definitely when the mass is moving at constant speed, the acceleration is 0. When it's just barely lifting the mass, we'll say that the acceleration is still approximately 0 and just hanging there. And so for me, I'm looking at this problem, and it seems like if I get an equation that relates everything together and I can just plug an acceleration value in, that'd be nice to have a really strong equation that works for all parts in this problem, and that will reduce the work for me. The first thing I need to do for torque analysis is to have a general sketch. We kind of have a general sketch here, but let me draw a little bit over to the side, just that we're going to have some sort of mass, and there's a free end of the pulley, and some force, some person maybe will come by and pull on the pulley and pull on the string and pull the mass up, okay? So when I look at that pulley, I'm looking at that pulley, it has two forces on it. It has the force from the tension on this side of the string and the force on the tension from the other side of the string. This will not be the same force. Okay, before, when you had a massless, frictionless, dimensionless pulley, you could assume that those two tensions were the same tension. But in this situation, there's going to be a net torque, and this force is pulling downward and this force is pulling this way, and so we need to denote that those two forces can't be equal in order to cause this pulley to rotate. The one has to be larger than the other. So I want this force to be larger than this force. I want the pulley to totally rotate in this direction. There's some sort of rotation, at least if there's not an angular acceleration. And so I'm going to call this T1 and T2. And I'm going to note that T2 has to be larger than T1 in order to get an acceleration or some sort of rotation in this direction. We can draw a free body diagram of the mass. I don't know if I'll need it, but I can draw it in. Here's the mass of the object. T1 is pulling upward on it. It's pulling downward on the pulley, but it's pulling upward on the mass. And there's a weight on the mass as well. And I'm going to note that its acceleration is upward if I need to relate that in there anywhere. Okay. Let's do a coordinate system. Let's say into the page is positive for rotation, such that when I rotate in the right-hand rule in the clockwise direction, I get positive into the page. That will give my torque for T2 a positive value and my torque for T1 a negative value. I'm just thinking ahead a little bit as I'm preparing to write some equations out. So we have a general sketch and extended free body diagrams for our objects in our problem. The next step in the strategy is to apply Newton's second law in the linear. We're still doing linear. So I'm going to take the net force and set it equal to ma. The only mass accelerating is the heavy thing that I'm trying to lift here, the 50 kilogram object. And when I look at it, it has two forces on it, the tension upward and the weight downward. So I can write that out. The T1 minus the weight equals ma. And if I solve for an expression for t, and I'm relating it to my other object in here, we're relating them, I'm just going to solve this for T1 real quick so that I have it, ma plus mg. So let's do Newton's second law in rotation on the pulley, I alpha. The net torque equals I alpha. On this side, just like the linear equivalent, all of the forces on the free body diagram go on the left side. Here, all the torques on this extended free body diagram goes on the left side. What I'm going to note is I have two tensions. Over here on this side, I'll have torque 2 minus torque 1 equals I alpha. They're pulling in two different directions, so they'll have opposite torques. Torque 2 will equal T2 times its radius, which is the radius of the pulley, and it's applied at a 90-degree angle tangentially to the pulley. So we'll have TR sine 90. Also for T1, very similarly, it will be T1 R sine 90 as well. It's being applied tangentially at a radius R. So when I plug this in, I get T2R minus T1R, and that has to equal I alpha. Okay, so we're getting closer here. I could take T1 and plug it in here, but I still wouldn't be able to solve for T2 because I don't know alpha. Alpha would be an unknown value. So this is the step where in the strategy I mentioned this, you will want to relate the acceleration of the object to the angular acceleration of the object. In order to relate the acceleration in this term to the acceleration in this term, we're going to convert it to the tangential acceleration. So I can say alpha equals the acceleration over r. I'm going to plug that in there. And also for a disk, we're going to approximate the pulley to be a disk. And I of a disk is 1/2 mr squared. So I'm going to plug that in there as well. So I'm going to pull an r out. R T2 minus T1 equals, okay, the moment of inertia goes in here, 1/2 mr squared, and then the alpha goes here, a over r. Okay, so I did some substitutions and I did some simplifications in order to get to this equation. What we're going to note is that a factor of r cancels with a factor of r here, and another factor of r, there's a factor of r over on this side and a factor of r on this side, and it cancels. And what we are left with is a relationship between T2, T1, and the acceleration. And I'm going to take what I have up here about T1 and plug it in down here. T2 minus ma, little ma, minus little mg, right? I have to subtract the whole quantity, so I get each term separately, equals 1/2 big ma, where big M is the pulley. Okay, so we're trying to solve for tension. I can get T2 over on one side. And let's see, I'll get 1/2 MA plus MA plus mg. This is little m, and you could simplify this if you want. A plus g, little m, a plus g. Okay, so now we have an equation that relates T2 to the other given quantities in the problem, and I can plug numbers in here. And notice this works for A, B, and C. All of them I can answer with this. If I have different accelerations, I just plug a different acceleration in. So if we do A, part A, we want the acceleration equal to 0, just barely equal to 0. And we're going to note that this solves part B as well. Okay, so we're doing double duty on this one. Acceleration equals 0, then I get T2 equals, well, this term is 0, this term is 0, so I get 0 plus m times 0 plus g, which is just mg, which is 50 times 9.8, 490 newtons. So this person over here would have to pull down with 490 newtons in order to pull up this 50 kilogram mass. And that may be obvious when we think about, does the magnitude make sense? Well, the acceleration is 0, right? We knew that T1 was just going to equal mg, and because there's no angular acceleration, if T1 is in this direction and there's no angular acceleration, then that equals T2, and so T2 has to equal T1 if there's no acceleration, and that's true for A and for B, 490 newton. Okay, so part C. We're going to note that acceleration is 4.9 meters per second squared. So I can take that and plug it in here. T2 equals 1/2 m, big M is 50. Acceleration is 4.9 plus little m, which is 13.6, multiplied by A, 4.9, plus G, 9.8. You can take all those terms and multiply them together and plug them into your calculator, and you get the force, this T2, that the person has to apply is 741.664 newtons. The last problem I've chosen is beam with a load of bricks. And you can see the general sketch over here. A long beam with mass and length given is held at the top by a cable attached to the building and secured by a pivot at the bottom. So that's what's going on. Here's the cable, and it's secured at the bottom down here. It supports a load of bricks, big M, connected 1.5 meters from the end. So I'm going to note that this is 1.5 meters here. And the total length of the beam is 8, which means from the pivot point to where that's being applied is 6.5 meters. We'll keep that in mind as we move forward in the problem. The beam and cable make a 20 and 35 degree angle with the building respectively. So you can see that over here in the sketch, 20 degrees here and 35 degrees here. The cable suddenly breaks. So at some point, the cable breaks and it's no longer there, and you can see that the beam is left free in order to fall. Find the angular acceleration of the beam at that instance. So in this orientation, the beam will have some sort of angular acceleration around that pivot point down at the bottom. Since the cable's not there, it'll just fall over. So let's do a free body diagram. We have an extended free body diagram here. I put on here a vector for the gravity, the weight of the big M, where it's being applied is 1.5 meters from the end, so this is 6.5. Another force we have going on is the weight of the beam itself, which will be applied at its center of mass. I always denote center of mass with an X. I'm going to draw the weight of the little m there. And it is then 4 meters from the pivot point. It'll be half the distance. We'll assume this is a uniform beam. Here's the geometric center, and so that's half the length. There's one more force going on. We don't have any X or components. The only other force we'd need is a force pointing upward, and this is what we know to be the normal force from a supportive surface. I can assign a coordinate system. That's my next step. Here's a plus y. I'm going to note that the angular acceleration is going to be, if I rotate in the clockwise manner with my right hand, I get my thumb pointing into the page. So I'm going to make into the page positive for torque, so I don't have to deal with any negative signs there. So the torque, well, about this pivot point P down here, the weight of the beam is going to cause a positive torque, and the weight of the bricks is going to cause a positive torque. So I'll go the torque due to little m plus the torque due to big M. That has to equal I alpha. While I'm here, I will write down I for the beam about its end, and this is like a stick or a rod. About the end will be 1/3 little m L squared. Okay. Let's write some terms out for the torque. The torque of the mass of the beam, well, I'm going to need the radius, the force, and sine of some angle. An alternative way, which I'm going to do here, is take the force times the lever arm. To find a lever arm, you draw a line of action through the force, so there's a line of action for that weight force, and when you drop a perpendicular line from the pivot point to that line of action. And in this situation, you can see it's really easy. So this would be the lever arm for this situation. I would take the weight and multiply by the lever arm. We know that this distance here is 4 meters. And according to the diagram, if this is 20 degrees here, then this has to be 20 degrees here. L is the opposite leg, so I can write L equals 4 times sine 20. So when I write out the torque for M, I will write out mg, that's the weight, times the lever arm, which is 4 sine 20. I'm going to do in a very similar fashion for the torque for the weight of the bricks. That'll be in big mg. Its distance is, here's its lever arm, right from right here. There's the lever arm for the weight of the bricks. It's a distance 6.5 from the pivot point. Its lever arm is opposite the angle given in the problem, so it will also get a sine term. So this will be 6.5 sine 20. I am going to set that equal to, let me move this out of the way. I'm going to set that equal to I alpha, which I know is 1/3 L squared times alpha. So there's my equation. I see there's a sign in both those terms. I'm going to solve for alpha very quickly here. I'm going to bring the sign out front, sine 20 times 4 little mg plus 6.5 big mg. You could even factor a g out there if you want. And you divide by 1/3 little m L squared. And you can plug in numbers through here. We have sine 20, 4 times 500 times 9.8 plus 6.5 times 2,000 times 9.8. And then we're going to divide that by 1/3 times 500 times 8 squared. The length is 8 squared. When you run this through your calculator and solve, you get 4.7135 radians per second squared. Okay, there's the angular acceleration. I didn't need to do a linear equation, that's fine, I just did the torque. Part B says, does the value of the angular acceleration increase, decrease, or remain the same as the beam falls? Justify your answer algebraically. So when it says algebraically, I want to look at the equation with just symbols in it. And so I can go up here and look at this equation here. Alpha is related to all the symbols in the problem, and I could put like a theta here to make it a more general equation. As the beam falls, the masses don't change, gravity doesn't change, the length doesn't change. The only thing that changes is the theta in there. So I can say that theta is actually increasing, right? It's becoming larger. It goes from 20 and then goes larger. So I know that theta is increasing. And alpha is dependent proportionally on theta. So I can say alpha is proportional to sine theta. So as theta increases, sine theta will increase. The maximum is at 90 degrees when sine theta equals 1. And that would give us the largest acceleration. So as the beam falls, it will increase because alpha is proportional to sine theta, and theta is increasing, which causes theta to increase, which causes alpha to increase. And that's an algebraic solution. I didn't have to plug any new numbers in order to figure that out. I just used the equation that I had already.